The next topic we're going to look at is characteristics of exponential functions. So maybe I'd like to start by just pointing out that most of the functions that we've looked at so far in the class are what's called algebraic functions. Those are things like f of x is equal to x squared. In these functions, you're usually plugging in a specific x value, and that x value becomes the base here, and the exponent in the expression that you're looking at is already fixed. And you can combine these functions together to form more general polynomials. So this is also an algebraic function, for example. But these are the sorts of functions that we've looked at so far. Today we're going to start looking at exponential functions. And these, instead of having a fixed exponent, will have some fixed exponential base. So 2 here will be called the exponential base. And then the exponent itself will be what's variable. So now we can plug in specific x values, and those will become the exponent in the expression that we're looking at. And in some of these cases, it will be useful to remember some exponential rules. So I'm just going to have us recall the rules for exponents. There's the addition rule, which says that if you have a product of two exponentials with the same base, then you can combine these into a single exponential with that base by just adding together the two exponents. And there's a similar rule for repeated exponentiation. So if you have 2 to some power and then you raise that whole expression to a second power, then you can evaluate that by just multiplying these exponents. So I would call that the addition rule and then the multiplication rule for exponentiation. And these rules can sometimes help. And notice that in the examples that we've looked at so far, these 2's are arbitrary. So the same rule applies if that 2 were replaced with a 7 or with an e, for example. So these rules hold for any exponential base. So the first thing that we're going to look at in this section is evaluating exponentials. So for example, we could look at evaluating something like 2 squared. Now this one we're already familiar with, but I just want to point out that if you really wanted to, you could use the addition rule that I wrote just above to evaluate this. So here I'm using the rule in reverse. I have a 2 squared, and I'm splitting this into a 2 to the first power times another 2 to the first power, so that would be a 2 times 2, which is 4. We've also already met fractional exponents like this. So if I have 2 to the 1/3 power, remember that the number in the denominator here is going to correspond to the index of the root that you should take. So this would be the cube root of 2. And I would be fine with you leaving your answer in this form, but you can also plug this into a calculator to get a decimal approximation. Now, in this section, we're going to start looking at more complex expressions. Like, for example, I could sort of combine these and write a 2 to the 2/3 power. Now notice that I can use the multiplication rule at the top of the screen here, again sort of in reverse. So I can think of this right side as being 2 to the 2/3 power. And I can split this into a repeated exponentiation like this. So that would be a 2 squared on the inside of the parentheses and then a 1/3 on the outside of the parentheses as an exponent. And you can see that these are the same because if we multiply these two exponents together, then we get back to the original expression. But then this would just be a 4 to the 1/3 power, which is the cube root of 4. And again, I'm fine with you just leaving your answer like that unless I explicitly ask for a decimal approximation. Now, these same principles can be applied to more complex exponential expressions. So for example, we know how to compute 2 to the 1.7 power. We can think of this as a fraction, so this would be 2 to the 17/10th power, and that would be 2 to the 17th power with a 1/10th exponent on the outside, and that would be 2 to the 17th power with a 10th root taken. And that's also something that you could just punch into your calculator. But what I'll say about expressions like this one, or like 2 to the pi, for example, For these expressions, you would usually just use a calculator. So it's important to see that we do understand how to compute exponents like this, or I should say exponentials like this. But for these more complex ones, it's fine if you just want to punch those expressions into a calculator. Now, when it comes to talking about what this exponential base can be, in all of these examples, I've chosen to just use the base 2, but you can use any base that you'd like as long as that base is positive and not equal to 1. So for example, 1/2 is also a perfectly good base. If we have something like 1/2 to the negative third power, remember that a negative power tells you to take a reciprocal of the inside. So we would take a reciprocal on the inside, and then the remaining positive power would apply. So this would be a 2 cubed, which is 8. Okay, so that's the basics of using these exponentials. There is a particular exponential base that we're going to focus on, which is called the natural base. The natural base is given by this constant e. E is around 2.718. The reason for focusing on this base will be a little more clear if you continue on into a calculus class. For now, I can't really justify to you why this is such an important base. For now, I just want you to know that this is a natural base to consider whenever you talk about exponentiation, and the number that it represents is around 2.718. So this is just a constant, but it's a constant that shows up naturally if you're doing something like calculus. So the corresponding exponential function would look like this, e to the x. So this is another important exponential function. Now, because e itself is 2.718-ish, we won't be able to compute expressions like e squared or anything by hand. For things like this, we would just use a calculator. And then the last thing that we're going to talk about in this section is graphing exponentials. So maybe just to return to our favorite example, let's look at graphing something like this. So I want to graph 2 to the x. To graph an exponential function like this, what I can do is the same thing that I can do to graph any function that I'd like. I can just plug in a bunch of specific x values to figure out their corresponding y values. So for example, maybe I can plug in x equals 1. So if I plug in x equals 1, then I would get 2 to the first power, which is just a 2. So that means that the point 1, 2 belongs on this graph. I could plug in an x value of 0. If I plug in an x value of 0, I would get 2 to the 0th power. Remember that anything to the 0th power is just 1. So I would end up getting 0, 1 should also live on this graph. We can plug in negative values as well. So this would be 2 to the negative first power. That would be a 1/2. So that gets us a third point. And in general, if we continued doing this, we would end up getting a graph that's roughly shaped like that. Now notice that you can plug in any x value that you'd like. So the domain of this function would be all real numbers. However, the range, if you squash this onto the y-axis, you'll see that the range is only going to give you positive outputs. So the range for these exponentials would be 0 to infinity. And then in our next